Folks, I'm back. I'm very sad to say that this is actually our last session for the conference. So, bit of a shame, but I think we're going to go out with a bang. We have actually one of our own D developers from Facebook here, Amaury, who's going to give us a little bit of a drill down into SDC, which he describes as a compiler as a library. So this should be a good one. Take it away, please, Amaury.
So yeah, this is a talk that is going to be about SDC, which is a project to propose an alternative implementation to the compiler. So I'm Amaury Sechet. There is my Twitter name. You can yell at me on Twitter and I won't see it, but I will read afterward. There is my website. So I will talk about SDC. So let's talk about me. We've been talking about D for 3 days now. That's boring. So we're going to talk about me. I'm a D user for years. This is a great language. I love it. But we have to admit that the tooling sucks. And, well, this is causing a lot of problems like frustration and air pulling and mass murder envy. So the thing is, building tooling in D is very difficult. Because if you want your tooling to completely work, you got to understand the whole language, even for very simple stuff. Because you have features like CTFE, Mixins, and templates. And if you're going to mix in some code into your D, then you have to run some CTFE. And you have to understand the whole code that you are going to CTFE before mixing it in. And if you want to do even something simple, well, simple like auto-completion, you have to be able to do CTFE to know all the symbols that there is and do the auto-completion completely. So those are great features, but those are also making the tooling fairly difficult to build. So I wanted to build a compiler as a library. So yeah, we need the compiler as a library to build some tooling, some static analysis stuff, some IDE stuff, code formatter, refactoring, whatever you think about. Like, whatever you may think about. To do all those stuff, you need to understand the whole D language because you need to do mixins, templates, and CTFE and all that stuff. We want to do also stuff like JITing D for REPL or, you know, whatever. You have CTFE anyway, so if you have a library that can do CTFE, you can send code to that library and JIT it. My first idea was to start working on DMD and extract a part of DMD to create a library from it. The problem is that DMD is written in C++. It's full of wizardry. There is some global state in it. And it's very difficult with all that stuff to actually like isolate some part of it, the working part, and make a library. Yeah, there is also plenty of weird stuff that come from the fact that it evolved from a C++ compiler, and some design you wouldn't do it that way, or at least I wouldn't do it that way if I would start directly writing a D compiler. So yeah, that is pretty much DMD. Let's try to write DMD. Well, not suitable as a library. Let's try something new. So there have been other attempts to do alternative compiler for D, and so far they have all failed. And this is something I wanted really to understand before starting my own stuff, because I don't want to start my own project and end up, well, the same way the other before and the other. So I got to understand why they fail. And basically why they fail is that they try to make the compiler like in the expected order. Like you do the Lexer first, and then you do some parsing, and you do some semantic analysis, and you do more and more stuff. The problem is that at some point you hit a brick wall, because you hit the exact stuff that are difficult for tooling, they are difficult for compiler too. So templates, CTFE, mixins mostly. Those are the difficult bits, and And you got to have like some architecture in your compiler that support that well. This is what have caused a lot of trouble of previous attempts, so I don't want it to repeat the error. So there was this project, SDC. I actually didn't start it. No, I'm a main developer of it, but this is not my project to begin with. This is a project from Bernard and Jacob. I don't even want to pronounce their name. I don't know how to pronounce them. The code base was overall pretty sane. At the time, they have a compiler that worked in a single pass, and that was showing its limits, so they needed some heavy refactoring in the semantic analysis. So that sounds like a good project for me to chime in. There was already like all the basic block that I needed, and I could start working on semantic analysis directly, and I decided to work on those hard problems that kind of made the other compiler attempt fail so far. Well, so far, maybe some other people will come with stuff, but. Okay, so a quick explanation of the type of problem you have. So this is like very, very simple code. You have a function that is declared within a static if with some CTFE as the condition of the if. So the usual structure of a compiler is that you have several paths, and each pass you do a part of the processing, and then in the other pass you do the next part of the processing, and so forth. Like you have 3, 4 paths, and then you emit some code. The problem is that you have to have completely analyzed foo to be able to do any CTFE, and you cannot even start to do anything with bar without you have fully analyzed foo. And that's actually a problem, because if you have several paths, that means, like, let's say you have 3 passes, you have foo must end the pass 3 before bar start the pass 1. And that kind of destroys the whole idea of having passes. So there is several solutions to that problem. Yeah, so so the first solution is to pass callbacks to the next pass. You say, well, I've done this and this and these symbols, I process them, but those and those and those symbols, I cannot process them. So here is the callback for me to call me back when I can actually process them. This is something that works. The problem with this is that, like, this is happening very, very easily and from the two ends of the spectrum. Like, some stuff must be completely analyzed to even start to analyze other stuff. So, so basically that's difficult to end up with a callback hell, to make it short. You pass callback all over the place. They get called, you have no clue why and in what order. When something fails for some reason, you cannot debug any of it because you have no clue or you end up there. This is callback hell. And I don't want it to go in that because the market is already taken by Node.js. So that was not that was not the right direction to go. So the second solution I tried was the deferred nodes. So basically, let's say I have an expression and I cannot compute it right now at some paces. So I will create a deferred expression with my expression in it. In it, there is my expression that I cannot analyze, and there is a closure that tells me how to analyze it. And that works pretty well. The main problem is that when you have a loop, like you have two stuff that depends on each other, and somehow that's not compilable. So what happens is that you create the first deferred expression, you create the second one, and then the second one have somehow evolved, because before you had the expression, but now you have a deferred expression. So there is like some progress that have been made. So the first one sees some progress, say, oh, I can process a little more, and you create like a new deferred expression from the deferred expression you have. And basically this is infinitively looping, but it still looks like you are making progress, and well, you end up never compiling your stuff and not being able to detect it. And that's pretty bad. So I came to build a scheduler, actually. there is some wizardry in it. But basically, the main idea is that I register some node in the compiler, in the scheduler. I say, well, you scheduler, here is my node, and here is how to process it. Here is the code you need to run to process my node. And then at some other point on the code, I say, well, I need that node to be processed. And the scheduler at this point knows either that the node has already been processed or, well, I got to run the code I have to process it. And that's actually pretty good. This has been working fairly well. This is the design that have been adopted. So let's explain a bit more how it works. When you have a symbol to be processed, or maybe several symbols, it expects a range of symbols actually. So you ask the scheduler to schedule your symbol, and you give it a delegate about what it should do about this symbol. And when you need the symbol to be processed, you just tell the scheduler, well, I require this symbol, and the scheduler can then schedule. That is his work. That is useful. The scheduler can keep track of all dependency. It knows when run and why. It can detect cycle. And it can give you information about that. So when you debug, it's not like the previous solution. When there is a problem, stuff don't get executed in the right order or whatever. You can know about it. You can put information into the scheduler so it can tell you what is wrong. That have been pretty successful. So each symbol is processed in a fiber. So the semantic analysis can be written linearly. And then you say, I require that stuff. The scheduler can then stop the fibers that not ready, interleave some other computation, and restart to the point where we were. That makes it very convenient to write semantic analysis. Because then you don't need to have many different functions that will analyze bits and bits and bits of a different node. You can just have your stuff, like to analyze my node, I need to do that, and that. Boom, done. And the scheduler will interleave the processing as appropriate. There is still a problem with what I have explained. It's for stuff like that. So you have an alias. It's a type of a function that takes an S parameter. And then you have the struct S that have one member that is this alias. And this should compile. But with what I've explained, it doesn't, because you have like the struct that depend on the alias, and the alias that will depend on the struct. So you have a loop. So there is an extra bit of information I didn't tell you yet that allow to get rid of this kind of problem. Actually, each symbol is processed. I have 4 steps of process. The first step is parsed. Then I'm just out of the parser. Nothing has been done yet. I'm ready to be analyzed. Then populated. Populated is like, I don't really know much about myself, but you can resolve identifier. Like if I have a struct, I can still resolve method names and stuff like that. Then sign. Sign is like, I know my type, I know my size, this kind of stuff. And then process is like, well, I have done everything, I'm ready to be fed to the backend and do code generation. There is 2 bits in each symbols that just store this information, and the scheduler can look at each symbol, see what step it's in, and go forward with that. So the require function have actually a second parameter. You can pass it whatever you want. And when you process a symbol, when you reach some step, you just can assign whatever value you want to the step, and you're good. The scheduler understands that and will schedule accordingly. So now we wanted the compiler as a library. So we want to explode SDC as it was. It was a monolithic stuff. So let's split it in 4. The first stuff is libd. So libd is everything that contains the semantic analysis, the lexing, the parsing, is like the stuff that understands D. Then there is libd. LLVM is the stuff that takes what libd generates, so fully analyze D code in some intermediate representation, and can generate code using LLVM, can generate machine code with that. There is SDC. So SDC itself, no, is very small. It's just a driver that say libd do that, libd LLVM do that, generate the stuff. I parse the command line, I parse the configuration file, and I do whatever I'm asked to do. SDC is pretty much small. And there is libsdrt, which is the runtime. So basically, that look like this. Fairly simple. Broad overview of all that work. What is the process inside this whole machinery? So to begin with, you have the Lexer that is mostly generated automatically. It's very similar to Flint. I don't know if you know about it. This is like C++ Lexer and like linter, actually. The password work on the token range that is given by the Lexer. It created an AST from that. The AST is made to be as close as the source as possible. So some tooling can work with some representation of the code that is very close to what is written in the source code. It means that there is like, often there is several different syntax that are semantically equivalent. Those have different representation in this AST. So yeah, it can be used by tool. Then there is all the semantic analysis, take the AST and generate an intermediate representation so it can be fed to the backend. And then there is code generation and optionally optimization if you want just before, depending on your compiler switch. So can you read that? Or is it yes? Well, that means it's too big. So basically that's all the Lexer work. Well, there is a lot of code that's been removed because like this is already quite an important piece of code. But basically you have some function that define what you're gonna do. So you have like the key or the prefix. So if I see like 0x, for instance, I'm gonna call the function lexNumeric because I know I'm in front of an hexadecimal number and the lexNumeric function take care of that. And so I return that. This is fed to like the giant Mixin of L that generates several thousand lines of code, which is there. There is the usual pragma message to debug the stuff because we have no real way to debug this kind of L. And then while here is how it's done, basically. It's pretty simple. You create the token, you put some information in it depending on what you have from the source, and you return the token, and it turns around and until the end of the input. Then to process the stuff, we have some visitors. Visitors usually are done manually in object-oriented programming, like you do your interface, that is a visitor, you have a virtual method in there for each kind of node you support, and you have your methods that implement the visitor and that define all those methods. The problem is every time you add a new node, you add a new method in the interface, you break all the existing visitors. And every time you implement a new visitor, you have to implement everything right away, because otherwise you don't implement all the method and the stuff is not happy about it. So this is a very inconvenient tool to work with, but this is how most compiler right now works. With this kind of stuff, we can like generate all the boilerplate automatically. This is much, much nicer. So basically what it does, it's a simplified version of the actual code, but what it does, it gets all the overload of the function visit of the class, the struct, whatever you feed it. And it analyzes the parameter of all those overloads. And depending on whatever you pass, it will choose the right visit function to call. And if there is no visit function to call, it throws an exception like this is not implemented. Yep, that's very convenient. On the other side, when you want to create a visitor, that's pretty simple. And that's make like, there is basically you encapsulate all the ugly code in there, and then you have nothing to do. Like you create your function visit with a dispatch, and you implement as much visit function as you want, and you are good to go. So if you add a new node, you don't have to break every single of your visitor. You can just add the new node, add it wherever you deem necessary and continue. That helps development greatly. I guess I don't have to sell you that much. There have been a lot of talk already about code generation. So there is one stuff that is missing. We need some advertisement to put on the web pages. So I prepared one. I think we should buy some space on the web. So, semantic analysis, that is the meat of the stuff. That is the most important part. You have AST node and you want to transform their in intermediate representation node. This is fairly simple for expression and statement. For expression and statement, you just take the stuff, analyze it, output another node that corresponds. For symbol, this is a bit more complicated because there is the scheduler that is involved. So all the declaration are transformed to symbols. Basically, the declaration is the AST node for a declaration, and the symbol is the IR node for a symbol. And declaration will be transformed into symbol during the semantic analysis. So the first step is the declaration visitor. It takes declaration, it creates symbol from them, registers them into the scope. It does some magic around compile time feature, and it registers them in the scheduler. Simple. And the symbol visitor have a function by type of symbol and does the semantic analysis of the symbol. So there is some code that show that work. Obviously, like there is only one case that the real file have plenty of visit function for the different construct you have in the language. But you can see that at the end it's relatively simple stuff and not that complicated to write. So the compiler is easy to extend for new stuff. Here we have a variable. When you encounter a variable, you don't know if it's a field or a variable because if it's in class or a struct, you have to make it a field, and it's not static. So you detect if you need to create a variable of a field. You copy the different state you have with the linkage, is already static, what is the visibility, all that. You select, you add to scope, and you select. So select, there is a bit of magic in there because you may be in a static key for something like that. But basically what the function select is registering the symbol into the scheduler. Broad overview. And then what does the symbol visitor? Once again, it's fairly simple. It takes the declaration and the variable. By the way, do you see this first if? Do you see what is in there? You know what I'm doing it like this when I'm testing for autotype. Why do I create a closure that returns some stuff? Do someone know? You actually have to do that, otherwise it doesn't compile. Nobody knows? Because vid.type.type, if you put it directly in the type ID, DMD believes it's a type. When it's a value, it's like some of those weird stuff. If you put just one identifier, that works. One identifier dot another, that's a type. But anyway, if this is autotype, you take the type of the value. Otherwise, you just analyze the value, do an implicit cast. If this is an enum, you evaluate the value to know what it is. And you're done. Step process, return the symbol, good, finished. And with all that, you have like everything you need to analyze variables. Another example, a bit more complicated because I'm missing like, well, this is just variable and this is the most simple stuff. So I showed roughly how struct is made. It's roughly the same stuff. Like you create a new scope for the struct. You create the type of the struct. You say this is the type of the struct. You create the Mongol prefix, so everything will be Mongoled properly. You use the declaration visitor to visit all the member of the struct. You require the member of the struct. You say you are processed, done. The fields are processed before, because then when you have all the information about the fields, but not all the member, you can say I'm signed. Like, I know what is my type, I know what I have in me, I know my size, I know like the type information. So the first step is just knowing what are my fields, and sign, and then I can say I'm signed, and then I analyze everything, and I'm done. This architecture has proven to be like very, very, very much simpler than the other two solutions I had. It's much simpler also than what is in DMD. It's much easier to extend. So that has been pretty good, and this is the kind of design that these allow that wouldn't be that easy with other languages. Like the visitor stuff, it's impossible to do in any language I know in a reasonable manner. So still a bit on semantic analysis. The code is written on a linear manner in every of the function I showed you. Like you say, I do that, I do that, I do that, and boom, I am analyzed. The scheduler figure out how to interleave all of that. So you don't have to worry at all about this kind of stuff. This is fiber-based. The scheduler can detect loops, so you just have to write what I need to do to analyze these precise symbols, and everything else is taken care of by like the underlying framework you're working on. Let's talk a bit about locations. Each location on each node, like each token on each node have a location. The location is basically where does that stuff come from. The location contains the index line, the index and the line of where does that come from, and the source. And what is important is that the source, it's an object, it's polymorphic, and there is different kind of source. The most common are a file source or a Mixin source. So my token either come from what I read from a file, or the information I have from a Mixin. And the source is in charge of formatting message for the user. This is pretty good because it allows for very nice error messages. In the future, this will be used for debug support. Right now, there is no debug support, sadly. This is a lot of work. And the big part of it is like it can show what is going on within Mixins. And you don't get those weird error messages where you say, like, you have an error in this file at line 1,200 something, and my file have 200 line, and I don't know what's going on. I think most of you already experienced that. That's pretty bad experience. So this is one of the stuff I wanted to improve. So let's take a little example. This is extracted from the test suite of SDC. So basically what you have a function. You have this function that returns a string. The string is the declaration of a template. Within this template, you have another mixins that create the body of the function. You mix that in, you call it, and actually there is an error in the code that is made on purpose for the demonstration. Here the developers, that means me, type TT instead of just T. So you make a typo or something. And this is the kind of stuff, when you work with mixins, you will like have a fair amount of trouble to find where does it come from. It would just say you like, there is this TT stuff, I don't know what it is, and by the way, I'm not showing you any source code for you to find. So basically, here is the kind of output you get from that. You have this, so you have where the error actually is. It shows in the source code, but it says, by the way, this stuff is not in your regular, it's not in your regular file. It comes from the mixins. And here is where the mixing is. So this stuff is expanded from the mixin. But this T-bar stuff is itself included from a mixin, right? You remember? It's there, it's called there, and you have the mixin in it, right? So there is a mixin that called a mixin. So yeah, this code come from a mixin, so you can unwind the whole stack, how you ended up creating that code, where it has been mixed in, and what does the code inside look like, and what is the error you have. That is much nicer than well, than what we have with the actual front end. So that is why it's implemented that way. CTFE. CTFE, the idea is to reuse the backend to JIT. We don't want libd to be tied to LLVM. Because if people want to reuse libd to do tooling, we don't want them to always have LLVM around. That's a big fat library to link in. So some people may not want to depend on it. So you have this evaluator interface, and libd LLVM provide one implementation of this interface. And the libd will call like evaluate this, evaluate that, and it expects a result. And the other way, that is just JITing whatever you ask him to compile, well, to evaluate. It's JIT.stuff, and it trains the result. That is good because it reduces a lot the work that is needed. Because if you implement something in the front end, in the back end, then you can JIT it already. You don't have to implement something extra, like in an interpreter or something. So that allows you to move faster and get actually stuff working with limited resources. So here is the function.ctfe. That is actually fairly simple. You create a function. Basically, yeah, what has happened is that you add a function, you create a block in your function. The most important stuff is that you create a return stuff with the evaluation of your expression. Everything will be generated from there with this visit method. You call it, you destruct. You can use like all the scope exit and stuff like that, make it very nice to work with resources that you must to clean up nicely. Because all that stuff, it's calling into C and C++, and you don't have any resource management in there. But that's pretty nice. Like you create the resources, immediately you can do scope exit. So that's one of the big killer feature of D. You can create a scope exit, and you know whatever will happen in there, when I'm done, I will clean up those stuff cleanly. SDC support exceptions now. It relies on its own runtime, libsdrt. It's able to throw, catch, and clean up. Clean up is like when you have something to do when you unwind, but you are not really catching the exception. Like running scope exit, for instance, that we just saw before, or scope failure, or destructor, or whatever, right? When you need to do something when you unwind, but you don't need to catch the exception. What is an addition compared to existing implementation is that it actually runs properly with foreign exception. Like your D code calls some C++ code and the C++ code throw. You cannot catch that exception because D doesn't understand C++ exception. But the exception will unwind properly and all your cleanup code will be run. So your destructor, your scope exit, and all that will be run properly on the C++ exception. I think that's a nice to have when you make C++ and D talk to each other. This is the kind of stuff you want to have. Finally, is lower down a scope exit because we are building a D compiler. We're not building a Java compiler or whatever. Like this is the reverse approach that what is taken in DMD, for instance, that convert everything into try-catch finally, like SDC does the exact reverse. It transforms everything into scope statement. There is, except the catch block, there is nothing in all that mess of exception stuff. I have some war story while developing that stuff. Because I wanted to use like good D, idiomatic D, use like the different feature that exist and well. That ended up causing some problems because they used to have a lot of bugs in the implementation. Some of them were really bad. Like for a while I had to, I was facing a bug that caused the garbage collector to collect live objects. That is truly horrible, and you take a fair amount of time before realizing what is happening, because that's really non-obvious. But the fix was simple. You can disable garbage collection. Your program takes a bit more of memory, but that is working fine. Bogus closure, so value in closure that are not set properly. Context pointer not copied, that is pretty good. Like you do a struct, you have a context in it because you passed an alias parameter or something. You copy the struct, everything is copied within the struct, but not the closure itself. So you have garbage where the pointer is. That is very funny. That has been fixed. Separate compilation, forgetting to emit some symbols, and then you link and there is stuff missing. Obviously, you can compile everything at once. You have all the symbols, but, well, that is taking 2.5 to 3 gigabytes of RAM. And sometimes you face the other bug previously mentioned, so you want to run DMD into like either Dustmite or Valgrind, and you enjoy. Those are very bad points, but I have a very good point in this slide, is that the last release of DMD was actually the first one that ran like perfectly out of the box. There have been a new release process that have been put in place that allow you to test easily what is going to be released, submit bugs, and get everything fixed. And so there have been a lot of discussion over the past release, like at least over the past 2 years, maybe more, over how we should do release. And the last one was a bit messy, but as far as I'm concerned, that's a great, great, great improvement over what existed before. So this is certainly something we should do. Like some people, I know some people have been complaining that it took too long to release the stuff. It was much longer than the one before. We can probably improve on that. It was the first one we did, but this process is working, so we can speed it up, but, well. So that's it for the war story. What is working right now? What has been implemented and works properly? Everything that is basic C-style programming is working properly. You can compile it, and that's doing good. Everything that is object, but no interface. Everything that is like scope statement. Exceptions, templates, Mixin, CTFE. Well, there is a small detail with CTFE. The concat operator is not implemented, which makes the whole use of CTFE, well. What you should not repeat where you go out of this room. A lot of error are still assertion in the compiler, and you won't get a nice error message, but you will get something horrible with a stack trace and everything. That's pretty bad. However, that's kind of low in the priority list because there is all those other stuff. There is a lot of faking going on, like the GC mallocs and never scan and never free. That's actually fairly fast. They have drawbacks in terms of memory consumption, but that's okay. For now. There is many feature missings. This is an non-exhaustive list, but that gives you an idea of how much work is still required. Closure is probably one of the biggest one, because you have to capture some variables, but there is like a lot of horrible stuff that happens. Like you can pass the closure as alias parameter to a template, and within the template there is a struct, and you have to get this closure value from the struct. They have to be stored in there. Or the closure itself may be a template that is instantiated somewhere else. That's the kind of stuff is very common, actually. When you use map, for instance, you always pass a template, almost always. And you may capture some stuff, but it will be instantiated somewhere completely different. So it's not where you analyze the function that you know what is going on, so you cannot capture at this time. This is actually a fairly complicated problem. The other one are a lot of work, but much less complicated. So the closure is actually my #1 priority, because this is the one that may end up requiring some refactoring in there. And the less you have other stuff, the easier it is to refactor what is existing. So yeah, associative array is not implemented. Destructor is kind of half implemented. They are not guaranteed to run all the time. Several array operations like concatenation are not implemented. That makes CTFE useless, but working, but useless. Static constructor and static destructor are not working. Operator overloading. UDA not working at all. Compile time reflection is not working at all. Type qualifier and attribute, in some case they work, in some case they don't work. It's kind of inconsistent. There is work. This is an ongoing stuff. There is work. Hopefully that is going pretty fast. Node, I have a pretty good framework to work with. As you saw, like adding new stuff is not a lot of code, and so hopefully I think I can get there. So here we are. That's the end of the presentation. So if you have any question about all the mess I presented you, that's right now.
Any questions? Yep, up the front. I think it's just me running the mic, so give me a sec.
Two questions. One was just wondering how long you have been working on this, just so I can get a good sense of how much longer.
Right now it has been roughly 2 years.
Okay, and you're probably about halfway through. But I guess now that you have the infrastructure in place, it might.
Yeah, I wanted to work on the infrastructure to begin with, because I knew that it was what other compiler I failed on. So this is what I wanted to tackle first, and this is actually a difficult problem. And not having everything else implemented was actually a bonus, because then if you want to change the infrastructure, you don't have a bunch of code that is existing that you have to adapt to the new infrastructure. And yeah, probably halfway through. Yeah, I think that's a fair estimate.
My other question was, have you been able to run any speed comparisons for the actual compilation? Like take things that you can compile and DMD can compile and like just make a lot of those copies?
Okay, so DMD is certainly faster. There is very little chance that I can go as fast as DMD for just even if I can get the front end as fast as DMD, it's still relying on LLVM, which is much slower than DMD backend. On the other hand, it produces much faster code. Yeah, that's pretty much it. Also, you know, like there is this stuff like, you know, first make it works and then make it fast. I think fast is important, but first make it work.
I have a comment on the live stream, which I'll just repeat verbatim. So, does running the cleanups, for example, on the C++ exceptions, preclude any optimizations based on no throw?
I don't think so. If you bin the C++ code, you can also annotate with on the D side. You can put the same annotations, and if you lie to the compiler, bad things will happen, because it have no way to check that you are doing something that makes sense because of the boundary between the language. But it's exactly the same than on the D side, except the compiler must trust you and cannot check that you are not lying. If something cannot throw in C++, you just mark it no throw, and you should be good.
Okay, any other questions? All right, so another round of applause, please, for Amaury. And I think Andre wanted to say a couple of words.
I begged James to hand me a microphone for just 2 minutes. We have planes to catch, homes to go to, thoughts to mull over. Just wanted to make a few closing remarks before I pass the word back to James for the logistics. This has been a very inspiring conference, at least to me. Seeing from your faces that it's been the same to you. Don't forget that this wonderful language is as good as the people who work on it. This is what it goes down to. This is where the rubber hits the road. It's as good as we make it. And I think it's become, it's fairly obvious at this point that these meritocracy-driven language, we've had talks here by people I had no idea they existed, some. I had no idea how good speakers they were. I had no idea how, anything about them, right? But it was based on the merit of their submissions. They gave a talk, and as compared to last year, for example, the talks have been a lot more about, here's how I use D to get some great work done for real, as opposed to, in the former years, there's been like, here's how I use D as a hobby at home to do some cool stuff. Not to say that cool stuff is not cool, but, when you put that cool stuff to real work, it becomes so much more interesting. So there's been a lot of work like that. And I'm seeing some growth. I'm seeing growth. I looked at the numbers. I've seen growth in numbers. I've seen growth informally. And I'm seeing good growth. What I hope this to become is exponential growth. I've seen some sort of a linear growth. We've had this good increase in, all key metrics, in all kind of subjective perception, etc., but it's been linear. And it depends on us, literally on people in this room, the 69 people or whatever who are like watching online right now, people who care about this language, it depends on, quite literally, it depends on us to make this linear growth into an exponential growth. So I wish that you go back home and reflect on the great thoughts and inspirations that this conference brought about. And I would like to thank you personally very much to each and any of you who I'm looking at right now. Thanks.
And don't really have much more else to say other than obviously thank you very much to all of the speakers. I know the amount of preparation that goes into preparing for a talk like this, especially those of you that are new to speaking. I know it can be kind of a nerve-wracking experience, but I think everybody did an awesome job. I'd like to thank the AV folks who've been kind of working really hard in the background to make sure everything's getting recorded, and it's all going up onto the Ustream, so there'll be videos for downloading, anything you missed, anything that anyone on the live stream missed. We have had people dialing in from all over the world. I keep saying dialing in. It makes me sound really old. No one dials into anything these days. But anyway, people who've been watching the stream, it's been a really good audience there as well as here in the room. Obviously, I want to say thanks to those doing the keynotes. We've had 3 excellent keynotes from Andre, Scott, and of course today Walter. So that was absolutely fantastic. But most of all, I guess I should thank all of you for coming. I've been honored to be a very small part of it and have a chance to see what your community's up to. It's really impressive. It's exciting stuff. So to echo Andre's words, please go out and make this into something awesome. It seems very, very exciting. So thank you all for coming, and next year, I guess. All right, see you there.